Hey there, and welcome. Every single motion in the universe, from a planet whipping around a star to you just walking down the street, it's all governed by some really fundamental laws. But what if I told you that how we observe that motion can completely change what we see? Well, today we're diving into the physics of perspective with a concept that's absolutely central to everything: frames of reference.
So to get started, I want you to imagine a really simple scenario. It's something that could happen any day, but believe it or not, it holds a fascinating puzzle that stumped thinkers for centuries and really changed how we see the universe. It's a tale of one event with two completely different stories.
Okay, so picture this. You're on a train, and it's moving at a nice, constant speed. You lean out the window, and you just drop a small stone. Now, what's the shape of its path as it falls to the ground? Just take a second. What do you think you would see? And maybe more importantly, what would someone standing on the platform see?
And right away we have a problem, an apparent contradiction. From your point of view on the train, you and the stone are already moving forward together. So all you see is its downward motion. To you, it looks like it falls in a perfectly straight line, right down to the ground. But for the observer on the platform, they see both things happening at once. They see the stone falling down due to gravity, and they see it moving forward with the train speed. And that combination traces out this beautiful, curved, parabolic path.
So, who's right? Well, here's the punchline. They both are. Neither person is wrong. Both of those observations are physically 100% correct. This is not a trick question. So how on earth can a single event have two totally different truths? Well, the answer isn't in what's being observed, but in the viewpoint of the person doing the observing.
To unlock this puzzle, we need what you could call the master key to all of classical physics. It's a concept that lets us translate between these different points of view and understand why both people, the one on the train and the one on the ground, are totally right. And it's called the frame of reference.
So, what is a frame of reference? Honestly, the easiest way to think about it is as the set of glasses through which an observer sees the world. It's their personal coordinate system, their personal grid of up-down, left-right, and forward-backward that they use to measure everything. The person on the train has one frame of reference, the person on the ground has another.
Now, as it turns out, not all frames of reference are created equal. For the laws of physics to work out nicely and simply, Isaac Newton realized we need to be operating inside of a very special kind of framework. You can think of it as a perfect, idealized stage where motion is predictable and follows his famous laws.
And this ideal viewpoint is called an inertial frame of reference. Just think of it as any viewpoint that's either completely still or moving at a constant velocity. So no speeding up, no slowing down, and no turning. In our little puzzle, both the train moving at a steady speed and the person standing still on the ground are, for our purposes, perfect examples of inertial frames. But here's a funny thing. Defining what an inertial frame actually is can be surprisingly tricky, almost circular. This little dialogue that Einstein and Infeld came up with shows the problem perfectly. See, an inertial system is where the laws of mechanics work. And how do we know the laws of mechanics work? Because we're in an inertial system. It just shows how fundamental and sometimes slippery these core ideas can be, even for the greatest minds out there. Okay, so here's the really crucial point. When you switch between any two of these inertial frames, some measurements are relative, but one thing stays absolutely the same. As we see here, an object's position and its velocity, those are different depending on your point of view. But its acceleration, the rate its velocity is changing, is measured as the exact same value by everyone. This principle is called Galilean invariance, and is the bedrock that explains why Newton's laws work perfectly for both the person on the train and the person on the ground.
All right, so we've been living in this perfect, clean world of inertial frames. But what happens when we break that rule? What if our point of view, our frame of reference, actually starts to accelerate? Well, that's where the laws of physics can start to feel broken.
I mean, think about being in a car. You know the feeling, right? The driver hits the gas and you feel this force throwing you back into your seat. But if you look around, what's pushing you? There's no giant hand, there's nothing actually there. What you're feeling is just your body's own inertia resisting the acceleration of your frame of reference, which is the car itself.
And this brings us to the other side of the coin, non-inertial frames. These are any viewpoints that are accelerating, speeding up, slowing down, or rotating. And if you're inside one of these frames, Newton's laws, as they're written, seem to completely fail. Objects start to accelerate without any real physical force acting on them at all.
So, how do physicists deal with this?
How do we make sense of motion in a world that's constantly accelerating and rotating? Like our very own planet Earth. Well, the solution is as clever as it is strange. They have to account for forces that aren't actually there. You might even call them ghost forces.
Now, these are officially called fictitious forces, or pseudo-forces, and they're not caused by any physical interaction like gravity or a magnet. Instead, they're basically mathematical inventions. They're corrections we have to add into our equations that only exist because our frame of reference is accelerating. By adding in these ghost forces, we can make Newton's laws work perfectly again, even from a non-inertial point of view. It's a really clever fix.
Two of the most famous fictitious forces are ones you are experiencing every single second simply because the Earth is spinning. The first one is centrifugal force. That's that outward pull you feel on a merry-go-round. It acts on everything in a rotating frame. The second one, the Coriolis force, is way stranger. It only acts on objects that are already moving within that frame, and it pushes them sideways.
Now, don't let the name ghost forces fool you. Their effects are massive, and they are 100% tangible. That constant outward centrifugal force from Earth's spin has literally caused our planet to bulge at the equator, and it actually makes gravity a tiny bit weaker there. The Coriolis force is why a dropped object doesn't fall perfectly straight down, but is actually deflected a little bit to the east. And most dramatically, it's the force that gives massive weather systems like hurricanes their iconic spin. This whole journey we've been on, from a simple stone dropped from a train, all the way to the spin of hurricanes, it all leads us to a really deep and profound conclusion about the nature of motion itself. And it forces us to question one of the most basic assumptions we have about the universe.
You see, Newton himself was convinced that there had to be some ultimate, unmoving background to the universe, a sort of master frame of reference he called absolute space. For centuries, physicists hunted for it. They looked for some fixed, cosmic stage upon which all the motion of the universe plays out. But every single experiment designed to find this absolute stationary point has failed.
And that leaves us with a final, fascinating, and maybe even a little bit dizzying question. The Earth is spinning. It's orbiting the Sun. The Sun is orbiting the center of our galaxy, and our galaxy is hurtling through space. If every frame of reference is only defined by its motion relative to some other frame, can we ever actually find a point in the universe that is truly at rest? Or is the very idea of stillness just an illusion that depends entirely on your point of view?